Hey everyone. I am at GDC. It is GDC week. GDC, for those who don't know, is the Game Developers Conference. It's the largest gathering of game developers in the world. It happens once a year in mid-March, typically, sometimes late March, sometimes early March, and once February. Once or twice it happened in February. Anyway, the Game Developers Conference is a place where I am extremely busy. I basically go there super early in the morning, and I'm there until, well, I just got home not too long ago. So I don't have time to do like a proper sort of deeper video, but I didn't want to leave you guys hanging. So this may be kind of a shorter, more ad hoc video, but it's something I've wanted to talk about anyway. It's going to be based on a talk that I gave at GDC last year, and so that's the idea. So that's what we got. It's going to be entirely theoretical. It's all math based. So that's what we do. And there's like a little demo kind of. Okay. So the topic is on normalized values. Normalized values. So normalized value is sort of defined as being something that's between 0 and 1, inclusive. So 0 and 1 are included in that. Normalized values are kind of magical in a lot of ways. They're used in tons of different things. They can basically act as a percentage. And that's kind of one of the powerful things about them. And they can be calculated from given any value as long as we know its maximum value. So for example, if I have 46 bullets left in my gun of 205, I can pull up this calculator and I can say 46 over 205 gives me 0.224 approximately, 0.224. This is my normalized value. And I can multiply this value by kind of anything that I want. I can take any percentage. I can say I have an 82% chance to do something. And I can easily calculate that into a normalized value, which I can then, multiply into whatever I want to get 82% of that thing. So, normalized values are used for tons and tons and tons of stuff. AI is very common. A lot of times we do scoring, we do utility scoring or whatever. And those scores are often in ranges of 0 to 1. Because, a lot of times in scoring, especially in utility theory, you're trying to get values that are the same scale. So that's another interesting thing that normalized values let you do, or at least these types of calculations. I can say, I have 46 over 205 ammo. But I could say, well, we use health, why not? I say I have 25 over 50 health. So my health normalized value is 0.5 versus this guy. It's easy to tell that I have, more of a ratio of health than I do ammo. And I can use that for decision making and so on. And then these can be, pumped through curves or whatever. I can have, what are they all? There's like those type, there's all sorts of, different curves and things that I can create. And that's a topic for another day. But here's the problem. A lot of times what happens is we have several normalized values that we need to kind of create some single value. For example, you might have someone, you might say, okay, I have some score. This is score 1. And I have some score 2 and some score 3. These are like AI decision scores, just for simplicity. And I just have a bunch of these, right? So, these are just different like decision factors. For example, this might be like health, and this might be ammo. So these are just different things that I'm weighing. I'm saying, I want to attack the player. How much health do I have? How much ammo do I have? There might be like distance, and so on. Like these could be other things as well. It doesn't really matter. So all of these things need to factor into a single score. What is the likelihood that I'm going to do this? And boil into a percentage, right? And these are all normalized values. So you might have, 0.2, or you might have like 0.91, and so on, right? These are all normalized values. So how do we combine all of this stuff, right? We want to have some magical thing here, some box that, I want to do this, where all of these guys come into play. And then out of this comes some, final score of, heart, whatever. Like this is our actual final score. So now, how do we make this happen? What's in this question mark? Well, let's think about a couple of things that we can do. And I'll kill this here. Let's kill this whole thing. So the simplest thing that we can do is we realize that, okay, well, I have a 1. 0 to 1, like a common sort of naive way of doing this would be, well, why don't I just multiply everything together, right? That's kind of the easiest thing to do. So I might do like this sort of thing, I equals 1 to n for each of these scores, right? So I might do this kind of thing. Okay, that seems reasonable, right? That seems super reasonable. The problem is that scores will constantly be decreasing. That's okay, but every score will be a penalty. So it means that, if I have these two scores, right, this guy and this guy, versus 5 scores, like the number of scores I'm throwing in here is gonna weight me down, because 0.5 times 0.5 times 0.5, right? So 0.5 times 0.5 is 0.25, and then times 0.5 becomes what would that be, 0.125, right? So it's just going to keep going down. For every one of these things, it's going to keep going down, no matter what these scores are. It could be 0.99999 that this score is going to go down slightly. So this doesn't seem good. This doesn't seem like it's going to work. There's a second method that I want to talk about. And we can look at some of the math behind this if we want to, because if we really want to dig into this, like I'll go over here. I guess I'll do it in green. We can actually look at some of this stuff, and I'll prove all this stuff in a minute. But for now, I'm just gonna kind of write it. Let's say that I have 1, 2, 3, 4. We'll do 5, and then this will kind of be our total, right? So I have let's say that I have this vector score of 1, 2, 3, 4, 5, just like I have, and then total. So let's say that I just have everything at 0.9, right? 0.9, because it's 0 to 1, feels like a good score. But the problem is if you actually multiply, we can do that, right? We can just go here and we can be like 0.9 times 0.9 times 0.9 times 0.9 times 0.9, right? That's right. So approximately 0.59, 0.59. Whereas if I only had a couple of them, 0.9 times 0.9, it's 0.81. So we're penalizing you for having more. If we have sort of an average score, and in my case, I'm going to say 0.5 is average, right? What is this going to look like? Well, and I have the calculations here, so I'll just write it in. It's going to be 0.031, which is an atrocious score, right? And this is all the sort of multiplication method, and that's just not going to work. So we just can't do this. This is just not going to work. Okay, so let's kill this. Let's create a new thing here. And so now what we want to do is try another method. Well, there are other methods. Let's look at. I'm going to call this method the makeup value method, and this is going to get interesting. So the makeup value does the multiplication, but it does the multiplication through a totally different way. In fact, I'm going to come down here. So the idea is that it's still going to multiply everything together. And in fact, the core algorithm is still basically this, where we have, and again, it's I equals 1 to n. And we say, whatever my score of I is. But kind of the magic of this guy is we're going to have some kind of makeup value for that guy, which in turn is multiplied by, again, the score. And so what this does is it just, because we know that we're going to get these diminishing returns, so we are going to try and create this sort of makeup value. The makeup value itself is calculated as makeup value of I equals, it's 1 minus the score of I times 1 minus 1 over n. These are multiplied together. So it's basically this. So, I mean, and we could go into some detail about like what each of these things are, but this is the basic idea. This came from, so I learned it from Dave Mark. And I think he learned it from, I don't remember now. Well, I learned it from Dave Mark, and in his talk he talks about it. In my talk I actually spoke about it as well. But to be honest, I don't remember where he came up with it, where he learned this from. Ben Sizer, that's right. Anyway, this is another method. This is another example of something we can do. And we can do this. This is fairly reasonable, and there's definitely I have some examples of all of this stuff. I'll show you in a bit. And it's better. So here's what I'm going to do. I'm going to come here. We're on layer 1, right? Okay. So let's grab this guy. And let's look at these exact same values. And we'll come down here. We'll kind of move this guy over here. Okay. I'll merge you down. So this is going to be, I'm going to call this, the makeup value. So I'm going to say, MV. So that's what this guy is. So all I'm going to do is erase these guys. We're going to use the exact same values. So really high score. Let's figure out what this value is going to be. Well, I'm not going to go through the whole math. We have it here, but it's 0.868. Hooray. But this 0.5, I mean, we're still, if we actually do this whole thing, it's still 0.168. I mean, it's still not good. So that's the issue. It's still the same kind of like, we just keep going to this well of despair and keep penalizing having multiple things. Okay. So these are different methods that exist. I want to circle in on like kind of the real method. I think that's probably the next sort of step to do is to talk about the real method. The real method is called the geometric mean. And you can Google this if you want to know the like gory details of this. The geometric mean is another method for doing this kind of stuff. It's specifically designed to, we can even just look it up. It's specifically designed to combine normalized values. So if you just go, geometric mean, I kind of recommend the Wikipedia page because it just sort of goes through it. We can dig through this thing. And it's, there's a bunch of math and stuff here that sort of talk about how it all sort of works and what it means and so on. And we can dig into this kind of as much as we want. But the basic idea, let's go back here. But the basic, we're still doing this sort of multiplication. So we still, because you got to combine them in sort of some way. So we still have this sort of thing of score of I. But we do this root, and so this is GM equals this. And there's a bunch of different ways that we can calculate this. Like this is one of them. Here's another one where we say the geometric mean equals B to the M. M. Where M is equal to, good God, it's something like, log, but it's the base B log, score I, this whole thing over N. Like, so, it just gets nuts, right? You can do all sorts of crazy stuff in here. But the results are sort of incredible. If I come back in here and I grab this guy again, let's pull this guy in here, and I can kind of come down here and pull this guy over here. Okay, cool, and I'll drop this guy in here. Yeah, so if I come back in here and, we have our exact same values, all 0.9s. Ready for this? The answer is actually 0.9. I guess I'll just leave it this color. All 0.5s, the answer is 0.5. It's that easy. Let's add some more, right? Because let's test this out with some more values. And I can just sort of extend this chart a little bit. What happens if we give it some like kind of weird values? I'm gonna do these in another color. So let's say like 0, 0.85, 1, 0.9. So here's one of the really nice things about normalized values and sort of a multiplicative method. One of the nice things is that if there's any 0 in there anywhere, the whole thing's going to be 0. And the cool thing is geometric mean maintains that. Because there's other methods, right? There's like, I could take like the average of scores, right? But it's like, let's just do this. This is just the easier way. So, okay, so let's look at another one. Let's just look at a bunch of arbitrary values, right? 0.5, so kind of an average score. A high score, another kind of average score. A very high score and a very low score. So I would expect this to be kind of middle of the range. The answer ends up being 4, 6, 8, right? So this is kind of the way that you want to factor in these normalized values. It can be really, really powerful to kind of see all this stuff. There's a bunch of slides that I did for this. So I'm just going to show a piece of it, which is this guy. This is from the talk. Because this just shows, what does this all look like? So I have 4 methods here. I have multiplication, I have averaging, which I showed briefly. I have the makeup value method, and then I have the geometric mean. So if I go, let's do this. There we go. Okay, so, if we look at multiplication, well, like we're just getting tiny values. Look at that. All 0.5s, these are just small values. If I'm doing an average method, I'm like, these certainly are good. This guy, It's okay, but we want zeros typically to blank everything out. This guy's okay. It feels maybe a little high, but it's okay. So that's the average method. The makeup value method is right out, right? So this is makeup value. That's not that. That's okay. This one's not great. At least it does the zero thing. This one seems right out, right? And then we look at something like the geometric mean. Blue's not really going to show up. Yellow. Geometric mean is here. We get 0.9, 0.5, exactly what you'd expect. This is pretty decent. And then this zero, we still get the zero as we multiply in. So, this kind of comparison chart is really cool to be able to see this sort of thing. I can kill this. On top of this, I just have a little, demo, basically, that I did. I feel like I can log this. I can sort of zoom this guy in, make it easier. And this is where I pull a lot of these things from. I can just sort of make these tests. I have these values. You can ignore these grayed out ones. These are just temporary sort of sum of log, average of log stuff that I need for some of these other guys. But these are the actual values. Oh, you have an error. That's fun. Yeah, it's a log parameter. So yeah, this is going to be 0 because there's a 0 here. So you can just kind of see some of these values and kind of what sense they make. And so I just built this spreadsheet. Kind of one of my tricks that I use all the time is I build little spreadsheets for this type of stuff. I actually think this is one of the ones that has actual code. Yeah, I wrote a little utility, the Dave Mark style of utility combination. I just wrote it as a function. Made life easier. Anyway, that's kind of it. So that's what I wanted to talk about. It's just normalizing and combinations of normalizing and all sorts of stuff like that. Kind of math heavy, kind of theoretical. I wanted to give you guys something so that you could see, so to keep the cadence of videos and things like that. But I think this stuff is really useful once you start getting into any kind of scoring or normalized values. Combining normalized values is just such a common thing in any kind of procedural content generation or AI or any of that kind of stuff. All right, as always, if you enjoyed this, give it a big thumbs up and subscribe and all that fun stuff. And I will catch you next time.